Now we're going to have three presentations from three very different speakers in very different fields, but all of them have some fundamental academic science behind them, which has been applied to some really interesting real-world applications. To start with, Professor Graham Machin. Graham is at the National Physical Laboratory. He has a very strong academic record as well. I think something like a couple of hundred publications, a lot of keynote speeches as well, so we should be very prepared for today.
Okay, so I want to talk today about transforming temperature traceability. Does anyone know what traceability is? Oh, I know you would actually. Okay, good. I'm glad I'm not teaching you things you don't know. I'm going to talk about what traceability is first, just to make sure you know what it is. So I wanted to say a few words about NPL. Hopefully most of you know NPL, and I'll then talk about measurement and why measurement is important. I'll talk about traceability in general, and then temperature traceability, because that's my technical area as well, and how it's changing from tracing to defined scale to allowing primary thermometry in process. And there's a big innovation chain we'll see as we go through the actual processes itself. So first of all, I'm Graham Machin. I'm head of temperature standards at NPL. I also have a role in decommissioning nuclear facilities as well. So I found myself 2 days ago standing in Sellafield looking at pile 1, where they were making uranium for the bomb in 1947, and I've had to take it apart. So I do quite a lot of interesting things as well. But we'll talk about temperature measurement today. So NPL is the UK National Measurement Institute. It's only one. It's been around for 125 years, 120th anniversary today, this year. I mean, there's 1,200 people or so distributed across the country, mainly in Teddington, but there are offshoots in these other places as well. And our aim is really to make sure that all measurements are done correctly around the UK and consistent with our international trading partners as well. The foundation of our measurements is, of course, the International System of Units. It started with the metric system. It started in the French Revolution in 1791, 1792. I love this clock. It's a decimal clock. One of the things that didn't quite catch on the metric system, but you can still see this clock. But throughout the 19th century, the metric system, the SI metric system slowly spread, particularly in Europe. And then in 1875, there was a big convention in Paris called, and they established what's known as the international, the meter convention. I've got a picture of that on the next slide as well. And 17 nations signed the meter convention to say that we are going to definitely adopt the kilogram and the meter as our SI as our units. Well, I'll just say the United States was an initial signatory of the meter convention, so they may go a little way to go yet still. But they're getting there. They're getting there. The modern SI system. Sorry, just talking about this. This is the meter convention. There are some interesting signatures of the SI original signatures of the meter convention. Britain didn't sign. Britain signed in 1884, so it took us quite a long time as well. Lord Kelvin tried really hard to make us metric. He got 7 million signatures from around the British Empire to try and make us metric, but some civil servant in Whitehall decided it wasn't a good idea, so it didn't happen until the 1970s, but there we go. So the meter convention, 1875, so its 150th birthday, going to be celebrated in Paris in June. The SI system is actually probably the most globalised thing you can imagine, because actually nearly all economic activity that happens is governed by the SI system. Over 98% of the global GDP in trade and all sorts of things is actually covered using the SI system. I wouldn't like to say the SI system drove globalisation, but it certainly facilitated globalisation. So here's the SI system in a nutshell. It's based on 7 base units: the kilogram, the metre, the second, the ampere, the kelvin, the mole, and the candela. And they're all defined in terms of either fundamental constants, you can see the constants here, or the conventional constant, and an atomic property of the second. And that's really how the units are defined. There are no artifacts in the SI system. So the kilogram is defined in terms of the Planck constant, for instance. you can ask me later why that may sound a bit strange. You can ask me later about that. Then all of the other units that people might derive are derived basically from these 7 units. So the kelvin was redefined in 2019, along with all the other SI units. The previous definition was in terms of the drip point of water. The current definition, which I guess won't change in my lifetime, and probably not even in my children's lifetime, or maybe never, is in terms of a fixed value or defined value of the Boltzmann constant, which has this value here. So no one measures the Boltzmann constant anymore, just like no one measures the speed of light anymore, because they're defined quantities. Why is measurement important? Well, you think about buying and selling, it's really important to have the right measures in liquid and in mass. You don't take your weighing scales with your kilograms to the supermarket to buy things, so you rely on the fact that the measurements are done correctly. You don't take your liquid measure to the fuel station if you have a liquid-driven car and just measure out your litres and pour it into your car because you trust the meters, don't you, on the fuel station or not. But you should trust them because there's a very strong infrastructure in the UK to make sure that works. Of course, the government's interested in tax, and so are we. And we want to make sure those measurements are done right so we don't pay more tax than we have to. And the government wants to make sure we pay as much tax as they want us to. So there you go. But of course it's also important for transport, from making sure the temperature in the engine's right and it isn't too hot and your turbine blade melts. No one wants that. Make sure the radiation monitors inside the cabin so that the crew aren't overexposed. Manufacturing is really important to get reliable measurement, particularly dimensional measurement, because bits of aircraft or bits are just made of cars or just modern manufacturing are made all over and brought here and assembled. For instance, just think of aircraft where wings are made in Bristol, the engine made in Derby. They're put together with a plane body in Toulouse. A large aircraft still has lots of shims in it to make it work. You may not know that, but some of them, there's nearly, I think sometimes nearly 1/4 ton of shims in aircraft, in a large aircraft, to make all the bits fit. So I was told by my dimensional colleagues, so it's quite a lot, but they're very heavy things, aren't they? Power generation, of course, nuclear reactors, you need to know the temperature inside a nuclear reactor quite precisely, or you need to turn the wick down so it doesn't get too hot inside, one or the other. And others. And of course there are loads of others as well, but all of these fields need reliable measurement, and it's all done through a concept called traceability. So really traceability is that you have national reference standards which are qualified by international comparisons. They're used to calibrate working standards which go from the National Measurement Institute to calibration labs. They then calibrate thermometers or calibrate sensors to the next level. They are then sent out to users, and that's the route of traceability, the pyramid of traceability. The SI unit, primary standards, essentially goes down to the measuring instruments. Quite a large number of steps, and the measurement uncertainty increases each time. That's really been the process of calibration and making sure that measurement's been done reliably around the country and around the world for really over 100 years. We want to change that. So I'll talk about some of the things we're going to do to try and change that. Short, basically making this go from the top, the SI units, to the measurement instruments, without having the steps in between. That's our objective over the next 20 to 30 years. So just in case Andy knows this, but maybe some of you don't, I want to talk about temperature traceability. So basically you have a route, you have the definition, which is established by the meter convention. You have the National Measurement Institute, which sets up the scale. So the scale, I will talk about why you have a scale and sort of go straight back to that in a few moments. So the scale in use around the world at the moment is the International Temperature Scale 1990. You then calibrate the thermometers against the scale. You send those to calibration labs, and then the user measures. They calibrate thermometers and they go to users who then measure T90, which isn't the same as thermodynamic temperature. It's close, but it's not the same as thermodynamic temperature. There's a reason for that as well. So the world's been using defined scales for about 100 years, maybe a little bit longer. and not measuring directly to thermodynamic temperature based on fundamental physics. And the main reason they've done that is because it's very difficult to measure fundamental temperature in a low uncertainty. So they do very careful primary thermometry experiments on fixed points. They measure the temperature of fixed points, and those fixed points are used to calibrate thermometers. So this is the ITS 90. I guess you'll get these slides. If you're interested, you'll be able to read as much as you like about the ITS 90 at the International Bureau of Weights and Measures website. But basically, the international temperature scale of 1990 goes from 0.65 Kelvin all the way through to the highest temperatures there are. And its purpose is this: it's really to set up a scale which has practical thermometers calibrated against fixed points, the slice of a fixed point of known temperatures, which gives you a precise and reproducible temperature. And they're exquisitely precise, so room temperature, talking about 0.1 millikelvin or so. So they're very, very good. You use devices like, mainly devices used in the middle is Platin thermometers to set up the scale. At lower temperatures, use the constant volume interpolating gasometer, some vapor scales, and at high temperatures, use Planck's law in ratio form. We'll come back to that in a few minutes. So why do they want to change? Well, if you look at this curve. This curve here is T, the temperature given by fundamental physics, whatever you want to use, be it gas thermometry or refractive index thermometry or whatever, and T90, which is what the temperature scale gives you. So if I had a thermometer calibrated by T90, it would be wrong from fundamental physics by these numbers of millikelvin at these temperatures, and then it sort of really accelerates out when you get above 300 Kelvin or so. So if you want to do global warming studies, it's absolutely essential that you do a correction to T, for instance, because a few millikelvin difference means the ocean holds an enormous amount more energy than you're expecting. So although a few millikelvin might not look very much, in some situations it actually makes a huge difference to your calculations. Also fundamental material studies as well, it can make quite a big difference in those things. So if you want to maintain that traceability I've talked about, you need to do regular recalibration. But what you really want to do is have, or what we're really working towards is have sensors that measure thermodynamic temperature that you can put in a process and you can forget about them, and they'll always measure it, whether it's 1 year, 10 years, 100 years. Whether it's in your phone, whether it's in a nuclear reactor, that's what we're in trying to do. But it's a process, so I'll tell you about the process we're working at now. So, yes, okay. Let me just go straight to this. So the first step really is to try and remove the temperature scales. So we have the temperature scales first up here. So we remove the temperature scales, and instead of calibrating to the temperature scales, can we get a link direct to the definition of the Kelvin through the Boltzmann column? And we do that, and then we calibrate thermometers direct to the fundamental thermometry, and then you do the same, the traceability the same after that. So you still do the calibration in the National Measurement Institute, but you do the calibration to T rather than T90. You get rid of the temperature scale. So I want to give a couple of examples. I'll go to talk about the first and third. So at high temperatures, so it's a bit small, but basically at high temperature at the moment, you use Planck's law in ratio form. So here's Planck's law in ratio form. You measure the spectral radiance of a known black body of either silver, gold or copper, with its temperature defined. You measure its spectral radiance with a thermometer. Then you measure the spectral radiance of an unknown black body. You see the shiny thing, that's an unknown black body. Then the only thing unknown in this equation, if you set the wavelength with a filter or spectrometer or something, is T90. So you can then solve that equation and move out to get T90, and then you can calibrate your thermometers. It's relatively straightforward, but it's really prone to error. Because you're extrapolating from a low temperature to very high temperatures. So we did a comparison recently with some colleagues in an NMI, which were remain nameless, and they were quite a long way off compared to the other people in the comparison, and they were not doing a correction for a linearity of the detection system. and that just caused the uncertainties to balloon at higher temperatures. So can you get ready for that? Well, our aim is to use what are known as high temperature fixed points. So you've seen the fixed points again. These are much smaller, they're about this size. Here's your black body radiator. And we've been using primary radiometry to measure the temperatures of these fixed points. They're metal carbon, mainly metal carbon eutectic, so they have a really nice flat melting point with an uncertainty of about 40 millikelvin to about 200 millikelvin or so at the highest temperature. So really low uncertainties for these sorts of temperatures. We just published in a paper last year the final temperatures of the last 4 of those. So what you can do then, instead of having low temperatures up here and extrapolate to high temperature and not knowing what the uncertainties are, you can then use 2 or 3 of these, realise their radiance in a furnace, and use Planck's law in a parameterized form like that, and have low uncertainties throughout the whole range. But because you're using Planck's law, you can also extrapolate as well, and the uncertainties don't balloon outside as well. So that's a really good way of getting low uncertainties. But it also means you can also not do it in the National Measurement Institute. You can just send these fixed point black bodies to calibration labs, and they know the temperatures, so they can do all that themselves. And that is in fact starting to happen even now. And you can either send, and they can either realise T or T90 depending on what temperature you put on the fixed points. I'm not going to talk about low temperatures, but similar thing, very complicated way of setting up temperatures. There's 2 scales, PLTS 2000, ITS 90. There's a number of ways ITS 90 says you can set up the scales as well. We make this quite complicated, and we're working towards making that much simpler. But I'm not going to talk about that. Just want to say a few words about the intermediate temperature range between 25 Kelvin and 1300 Kelvin. There's a poster outside talking a bit more about it at the moment. But when Daniel said to me, send some posters, not everyone's going to send posters, so I'm sorry there are so many posters from me out there, but feel free to have a look at them. So there's a project, a European project running at the moment, and it's really focusing on really 4 Kelvin to 1300 Kelvin, but really our main aim is 25 Kelvin to 1300 Kelvin. And really the aim is to take advantage of the Kelvin redefinition using gas-based type thermometry in this particular case to try and see, can you disseminate thermodynamic temperature from the NMI to the user at those uncertainties. And our real aim is to have a first trial ever, because no one's ever done it before, of disseminating, is doing a calibration of sensors and then sending those sensors to people with T on, and retaining uncertainties as good as ITS 90 from the range 4 to 25 Kelvin, and from 25 Kelvin to 303 Kelvin as well. So we're in this has just been going for just over 18 months, so we're in the process of starting to do the measurements now for these things. But it's a long-term aim. So these things are will really just set up the framework for actually being able to do it in up to 300 Kelvin. And then the next thing to do is do an international comparison to see that it can really be done. So this is sort of about a 5 to 7 year time frame. To go to 300 and 1300 Kelvin, as you'll see on the poster, is an even more difficult challenge for a number of reasons. You should ask about if you're interested later. But we're aiming to do that in the next, set up the process to do that in the next 5 years. So we're talking about a time of 5 to 15 years to do that sort of thing. So I think mid-2030 is the earliest before we can do most of that from a National Measurement Institute. So it's not that innovative, but innovative for my colleagues. They feel uncomfortable, some of them feel uncomfortable already about what we're going to do what we're going to do after you set up this, anyway. I'm sure they'll be doing other things. So there's another approach which I think is more disruptive, and let me go to that. So instead of having calibration labs, why can't you track from either the definition of the Kelvin to a sensor in the process, or at least the temperature scale to a sensor in the process, and have the sensor do the calibration itself for you. And that's what we're working on now. We're getting close to be able to do that. So the key to doing that is to shrink the fixed points. So the fixed points of this are, you can see, about 40 millimeters or so in diameter, and we've been shrinking them down, so now we have ones which are less than 4 millimeters in diameter. I was quite amused by hearing that when my colleague showed one of these to a Korean visitor, he burst out laughing. He didn't believe that was really a fixed point, apparently. It really is a fixed point. And the aim is really very simple. You have a sensor, it could be a thermocouple, it could be a resistance sensor, and you incorporate within the sensor one of these very small fixed points. There's quite a lot of difficult things you need to solve to make that happen. And then basically you interrogate the actual melting point or the freezing point each time the sensor passes through that point itself. And you know what the temperature of the fixed point is. Okay, this is cobalt carbon, so its temperature is around 30 to 24 degrees C. It tells you that the thermal voltage of this thermocouple is this amount at that temperature. And then you can slide the whole reference table up and down, so it's approximately linear for a few hundred degrees either side. It's not completely linear, but it's approximately linear. And you can slide the reference table up and down and do a calibration in process. And straight away, that allows you to really make sure your processes run optimally all of the time. It means you can make nuclear fuel optimally all the time, rather than make nuclear waste if the temperature sensor goes out of calibration too far, for instance, which has been known. So we're actually working with a company called CCPI Europe in Rotherham, and they're actually commercialising this approach, and they've got a number of these devices now out in heat treatment furnaces in Britain and in Europe, just giving trials. The difficult thing actually with this is actually getting some software to identify the melting point. You can see it easily. Even in noisy, this is very good data by the way, even in very noisy data, the human eye can see it. But actually, to get a piece of software to see it, it's very, very difficult. So we're actually having to use some machine learning to actually identify this. So even when you have a very complex and difficult measurement set, you can still see reliably the actual melting point itself. There are some tricks to make it work, which I haven't told you about, again, which you could ask me about. But really, the thing we really want to do is this, which is, can we get traceability to primary thermometry in the process itself? And this is really disruptive, because you don't actually end up having traceability back to the National Measurement Institute. You actually have it linked into the process itself. And the key is to break the fact that you don't have the sensor calibrated, you have the measurement system calibrated. If you've got a sensor in any industrial process, it's actually very difficult to retrieve it. If it's a thermocouple, there's almost no point in retrieving it anyway, because you can't recalibrate the thermocouple. Base metal one anyway, you have to just go to a new one. If it's no metal one, it's a bit different. But you could put it in a nuclear reactor, or you could put it in a very hostile environment which has contaminated it, or you could put it in something that's made it impossible to bring out of the system because it's become swollen. So what do you do in those situations? Well, our aim is not to have a sensor that needs recalibration, but to have sensors that are linked to the physics of the situation, and therefore don't need the sensor calibrating the measurement system itself. So that's this side here. So the dream is really to have people to link directly to the bottom, the redefinition, the definition of the Kelvin, and bring it down to measuring in the process, wherever it might be, whatever that process might be, measuring T, thermal temperature, using practical primary thermometry. That's a big ask, but that's what we're working on at the moment. I want to talk about three of these. I've got posters of two of these if you're interested, on the Doppler broadening and the ring resonator thermometry out there as well. So let's just talk about Johnson noise. So everyone knows, most people know about Johnson noise. If you're a certain age and you used to turn your radio on, they used to hiss, and that was the Johnson noise in all the electronics. Digital radios don't do that anymore, unless there's something wrong with them. But old radios used to do that. Basically, it's voltage, mean square voltage, and basically have a simple equation: electronic bandwidth, resistor, Boltzmann constant, temperature. If you know what the resistance is, and the bandwidth of electronics, you can determine the mean square voltage. You can determine the temperature from the mean square voltage. The biggest issue with Johnson noise thermometry is the signal is extremely low. It's sort of nanovolts, and in industrial situations, that's a very challenging measurement to make. If you measure in metrology, people have been using Johnson noise to measure T with very low uncertainties, but then you need very special rooms which are completely shielded from exterior electromagnetics. You need power sources, which are basically enormous batteries inside the room to power that. So my Chinese colleague, when I visited his lab, basically his lab could run his experiment for a couple of months and the batteries inside the room. And it's a very long experiment. And that enabled him to get to uncertainty of around 4 millikelvin or so without averaging. Turn it around, if you don't want low uncertainties but you want long-term stability, if you can tolerate target uncertainty of 1 Kelvin, which is what most people in the industry are getting, or worse, you can really simplify the measurement system. And instead of having a room full of equipment and having to shielded and isolated, you can have something which is handheld like this. This is being made by a micro company called Metrology with help from NPL. And you can actually make a Johnson noise thermometer that you can insert in process that works in real time. And we've got a lot of people, big companies, interested in deploying these in various situations. Looking at the names, you can understand where they might be. Okay, so Doppler broadening thermometry is also a very interesting technique. So you have an optical cell. You basically shine a laser light through the optical cell. The cell contains atomic species, maybe cesium or rubidium, or even this molecule, or it could be a molecular species. You basically need to target a particular line, spectral line, and you scan the line, and by measuring the half width of the line, you can determine the temperature of the vapor, the gas. If you want to do it with low uncertainties, you need a lot of passes, and this, for instance, is a Doppler broadening thermometer for primary thermometry. You can see, you can get a sort of sense of scale for it from the hand that's there. And if you're very, very careful and take many tens of thousands of spectra and make it stable for very long periods of time, you can get uncertainties of around 2 to 5 millikelvin if you're really, really careful with that. And you have an optical bench, which is enormous, covered with lots of optical equipment. So if you turn it around and say, can you tolerate an uncertainty of 1 Kelvin in the process rather than needing 0.01 because you're doing the calibration at the top. So if you're doing the calibration at the top of the chain, then doing lots of steps, you need low uncertainties. If you say we're going to trace straight to the physics and go straight to the process, you take out all those steps, but you're still getting the same uncertainty that you're getting at the bottom, which is the target. So we're working with, I've got some PhD students working at Strathclyde University, and our aim is to really build a small-scale practical Doppler broadening thermometer in the next 3 to 4 years or so. So we have a small optical cell. It's got a target atom inside. At the moment it's rubidium, just to practice, but it probably won't be rubidium in the final cells. And we basically have small cells. These are magnetometers, but they can be used as well for Doppler broadening as well. And the aim is really to have a fibre-coupled system which you can have, which looks just like an ordinary thermometer, a nice metal long sheath. You can put it in your system and forget about it. And the nice thing about that is the calibration is done by frequency. So you could use this on Mars. You can do a time transfer signal to a frequency to calibrate the measurement system, and it doesn't need any human intervention to actually make sure it continues measuring correctly. So just a paper just being published on that. Then the final thing I want to talk about is ring resonator thermometry. So here we have a relatively simple equation which links the refractive index related to the frequency and the signal. And this is a very simple, relatively simple, they're small things, but relatively simple. So we are starting with small devices. You can sort of, I'm not sure if the scales, this is the scales on here. They're just a few tens of nanometers in diameter, so they're quite small. And the thermometer works like this. You have two rings that are evanescently coupled. You send a light, usually a laser light that goes through the waveguide. And light gets coupled into this ring. So that's the activator. And then the second ring is the thermometer. And when you hit a resonance here, photons then tunnel across the weak link and set up a resonance in this ring. And then you have a detector detecting the frequency. And then as the temperature changes, the resonant frequency changes, the diameter of the ring changes, the refractive index changes, and so as the frequency changes, you can determine the temperature. That's effectively how the principle works. At the moment, people have done a lot of work using silicon, because silicon's easy, but you have to link the activating signal, you have to have a fibre-coupled device, and to detect it, you have to have another fibre-coupled device, and that's very complicated because you have to both glue them in. It's a mechanical connection. It's quite a difficult connection to make. Or you have to have very clever alignment with mirrors, the micro mirrors in the cell, to send the light in, and micro mirrors in so what you really like is an integrated device. So we're not working with silicon. We're using 3,5 materials like indium phosphide, because if you use indium phosphide, you can then microfabricate on one integrated chip the actual detector, activator, and thermometer just by tuning the composition. And that's what we were planning to do. So my PhD students have got to the point where they've worked out how to microfabricate these rings really exquisitely in indium phosphide. And the next year they're not hoping, they will be manufacturing activators and then detectors. And the aim again is by 28, 29 to really demonstrate on-chip temperature performance using active ring resonators. And again, because it's linked to that fundamental equation of physics, you can then have true thermodynamic temperature in your phone, on your computer, in your data center, in whatever chip. You actually need to know the temperature of. And that's really important because at the moment, the chips, you feel your phone gets warm when you're using your phone, but the chip's thermometer is a long way removed from the chip itself, and they don't know very well what the temperature is, so they put a big safety margin in to stop your phone getting damaged, which you're very grateful for. But if you're measuring the temperature on the chip in real time, you can let it run a bit hotter and squeeze more CPU out of it, which has a lot of implications for the data centers, for your computers, and for defence and other things as well. Anyway, I think I've said most of those things as well. Just, again, there's a poster out there telling you a bit more about some of the things that we've been doing. So I've really talked about temperature traceability, about where it is at the moment, where it's going to go in the short and long term, both changing traceability from the National Measurement Institute to thermodynamic temperature. The fact that I think the self-validating sensors will become ubiquitous in the next 10 years, probably for acting as reference points in sensor networks rather than replacing all sensors. But I think developing in situ practical primary thermometry will be the way to go, and will probably be there in the 2030s, 2040s or so. So these ones, again, of course, are linked to frequency. So again, you don't need to worry about removing any sensors or anything. You can do the calibration of this detection system via frequency. There's some more papers, which again you can see on the PowerPoint, which you can distribute if you're interested. And I need to say that because the European Union did fund some of it as well. Okay, thank you very much.